Hi everyone, welcome to this presentation. This time we are going to see how to do frequency analysis using WinPython. For those of you that are not familiar with WinPython, you can watch this video, WinPython number 1 introduction, which is available in my YouTube channel. In this video, we are going to see how to obtain Bode plots of a plant and compensator of a buck converter. Then we will see how to obtain the Bode plot of the loop gain, calculate the phase and gain margins of the loop gain, obtain the Bode plot of closed loop system, and finally obtain the step response of the closed loop system. Okay, then remembering the system that we are working with is a buck converter like this one. We have analyzed this converter and studied this converter in previous videos. You can check this one, LTspice number 6, to see the open loop frequency response, how to obtain this frequency response using LTspice. So this buck converter behaves like this plant, including the response of the PWM modulator, which is 1 over BPP, which being BPP, the peak-to-peak value of the ramp waveform used in the modulator, and then the response of the buck converter, GS. And then we have a second order response, as we have seen, including one double pole here at the frequency Fp, and then 1 0 due to the series resistance of the output capacitor, okay, which in this case, and this pole and zeros are at 7.1 kilohertz and at 106.1 kilohertz. Okay, for more information you can watch this video, LTspice number 6. So the first thing that we are going to see is how to obtain the buck converter transfer function. So for this we need the mathematical expression of the transfer function of the buck converter, okay, in which we have the duty cycle as the input and the output voltage as the output, and then if we go to the literature, then we can find this expression here in the Laplace domain in order to get this transfer function BO over duty cycle. I have obtained this expression from this reference here. Okay, so you can get more information on this here in this publication. So once we have the mathematical expression of our buck converter, then we can go to WinPython and then implement some code in order to represent this transfer function. So here we are showing how to obtain the Bode plot of the transfer function in WinPython. So we can see that we are importing some functions for the libraries. Then we are defining here the Laplace variable s equal to the transfer function of s, which is the easiest way, I think, to work with transfer functions in Python. Then here in this part we define the different parameters of the buck converter: input voltage, output voltage, resistance, load resistance, duty cycle, inductance, inductor series resistance, capacitance, output capacitance, and a series resistance of the output capacitance, and then the value of the peak-to-peak voltage of the ramp, okay, used in the modulator. So with this we can implement this expression here, which is the plant's frequency response, which is the gain of the modulator, 1 over BPP, and then all the response that we have here, GS. It's just a matter of writing here this expression. Note that we can use here the backslash. With the backslash, we can separate into lines, the expression, and then make it easier to read it. Now, in order to obtain the Bode plot of the plant, then we have just to use this function, which is Bode plot, which is in the control here in the control library. Okay, so we have imported here tf for the transfer function and also Bode plot. So Bode plot is a function in which we are going to give the expression of the transfer function that we want to represent in GP, and then we have several other parameters. For example, if we want to represent the gain in dBs, then we select here dB equal to true. If we want to use hertz instead of rad per second for the frequency, then we select here hertz equal to true. Then we provide the limits for the frequency, in this case from 10 hertz to 1 megahertz. Note that if we select here hertz equal to true, then the limits here are in hertz. Otherwise, they will be in radians per second. And then here, omega num is the number of samples that we want to have in the whole range. Okay, so in this case, we are going to get 100 samples. So now we can open our WinPython program and see the results of this script. So here we have our script here. We can see that I have divided now the different scripts in different cells, so we can operate with each cell separately. So here we have these expressions that we have seen right now, and then we can just execute this first cell by clicking here on this button here, run current cell, and then we can see the result corresponding to the plotting. For this we go here to plots, click here, and then we can see here the corresponding plot, the magnitude on the top and the phase at the bottom. So we can see that it corresponds with the representation that we have seen before with 0 dBs and a pole here, a double pole at around 7 kilohertz, and then a 0 at around 100 kilohertz. Now we can see also the phase in degrees. So the other possibility that we have to do the Bode plot is including the data output. For this, we can include, before calling the Bode plot function, these expressions here. Okay, magnitude, phase, and omega. Okay, because the output of this function, Bode plots, are these three arrays, and this with these three arrays we can get the value of the magnitude, the phase, and also the frequency. And then later, if we like, we can print the different values for the different samples. For example, here for the sample number 70, then we can print the value of the frequency, the gain in dBs, and also the phase in degrees. Note that we have to do here some conversions because the omega comes in rads per second. Okay, so we divide here by 2 pi. Then the magnitude is in per unit value, so we obtain here the value in dBs, and also the phase comes in radians, so we perform here the transformation to degrees. Okay, multiplying by 180 degrees and dividing by pi. Okay, so we can see here the result in this case. So for this we are going to comment this line here, so we can select the line and then right click, and with right click, sorry, do it again, select the line, right click, and then we can select comment, and then I'm going to uncomment these lines here. Again, right click and comment, and then we have here or we are calling here our function, including the output. Okay, for more information about each function, we can hover over the function and then click here, and then we will get more information here on the right part of the screen, the different parameters of the function and also the outputs. We can see that the function returns the magnitude, okay, the phase in radians, and the omega in radian per second. okay, the frequency. So let's see now what happens when we execute this cell now by clicking again here, go to plots, so we can see again the plot, and now here on this line on the console we can see the values for this sample, the sample number 70, which corresponds to a frequency of 34.3 kilohertz. The gain is minus 28.5 dBs and the frequency is minus 138.5 degrees. So this is something like in this point, this is 10 kilohertz, 20, 30 kilohertz. So this is the value for the phase, close to minus 135. And then for the gain is this value here below minus 20. Okay, so it is minus 28.5. Okay, so it corresponds to this value. So this is a quick way to measure the different values in our plotting. So now we can go back now and see the representation corresponding to the compensator and also to the closed loop response of our converter. Okay, for this we are going to use this PI compensator as we have seen previously in this video. You can watch this video, LTspice number 7, and in this video it is presented how to obtain the closed loop frequency response of our converter using LTspice. Okay, so we have used this PI compensator with this expression here and with this frequency response that we have seen before. So in order to see the frequency response using Python, then we include this new cell in which we are including the values of R1, R2 and C2. We have also calculated these values in the previous video. Then this will be the expression corresponding to our compensator, okay, this expression here. And then we just call the function Bode plot in order to represent the frequency response of the compensator. Okay, so let's go back to Spider and we can see here in this part here the cell corresponding to the plotting of the compensator. Okay, so we just select this cell and then click here, okay, to run this cell. So we can see here on the right the response of our compensator. Okay, so we can see that it has a pole at the origin, so this is slope is minus 20 dBs per decade, and then we have a zero around here, this frequency which is around 7 kilohertz, and then we have the flat gain at high frequencies. Okay, and for the phase we have minus 90 degrees, and then because of the effect of the zero, then we go back to 0 degrees at high frequencies. So this is the plotting of the compensator. So now let's go ahead and see the response of the closed loop by plotting the loop gain of our system. Okay, so this will be the block diagram of our system, and we have seen how to obtain this in LTspice in this video, LTspice number 7. Just remembering that our plant is given by these two blocks, 1 over VPP times GS, which is the response of the buck converter, and here is in red with the double pole at FP and the 0 at FZ. And then we have in blue the response of our compensator, CS, which is this block here, and then we have a gain for our sensor H equal to 1. So the complete response of the loop gain will be the product of all of them, which is the addition in dBs, and it corresponds to the green line here. And in this video, LTspice number 7, it was calculated these values for the compensator, obtaining the different components R2, R1 and C2. So in order to obtain the loop gain TS in WinPython, then we have here our system, and we just select here H equal to 1, the loop gain T, which is the product of GP, C and H, and then just the representation of the Bode plot as we have seen. In this case, because we are plotting the loop gain, it is interesting, maybe if we like, to show also in our representation the phase margin and the gain margin in the plotting. Okay, so in this case, this function Bode plot can do this if we include this parameter here, margins equal to true. So in this way, we can show also the phase and gain margin. Let's see this. So this is the cell corresponding. So with this cell here, we can execute it. Let's say, for example, now we are going to select margins equal to false in this case to see only the plotting. So we can do the plotting here, running this cell, and then we can see the magnitude and the phase corresponding to the loop gain, which are quite similar to this representation here in green as expected. So here we have around here the crossover frequency, which was around 5 kilohertz as we have seen, and then this will be the representation also for the phase. So if we select here in margins equal to true and execute, then we can see in our plotting, okay, this is a simplified plotting, but now we are showing the gain margin and also the phase margin. In the case of the gain margin, there is no gain margin. The gain margin is infinite, and there is no frequency for the gain margin because our phase in our system is never reaching minus 180. And for the phase margin, we get 53.94, more or less 54 degrees as expected, and as always we have seen this in our previous videos. Okay, so this in line in black is showing the phase margin and the frequency at which we reach the crossover point, which is around 5.1 kilohertz. Otherwise, if we want to have the correct representation here, complete representation with more accuracy, then we can use this function, margin function, which is included in the control toolbox. Okay, so we are importing here the margin function, and with this function we can obtain everything. We can obtain the gain margin, GM, the phase margin, PM, the frequency at which we get the gain margin, WCG. Okay, so this is the frequency at which the phase is equal to minus 180 degrees, and the frequency WCP for the phase margin, which is when the gain reaches 0 dBs. Okay, WCP. So with this function we get all of them. In this case, I am only plotting the phase margin and the frequency of the crossover frequency for the phase margin, because the other, as we know, we are never reaching the minus 180 degrees. Okay, so by executing this, then we can see here on the console, we can see the phase margin around 54 degrees and also the crossover frequency around 50.1 kilohertz. So now we can go ahead to our presentation and obtain the closed loop response of our system. In our system, we know that the closed loop response is it has this expression here. It will be CS times GPS, the product of this part of the block diagram, divided by 1 plus the gain of the loop, the product of GCS, GPS, and HS, and this will be equivalent to this block here, which is the gain of the closed loop. So we can obtain again the representation, the Bode plot for this closed loop gain by using the same functions that we have seen before. Okay, GCL in this case will be expressed like this: CGP divided by 1 plus CGPH, And then by calling the Bode plot function, we can get again our representation. And if we like, we can get the values corresponding to the different points. So let's see now this here correspond to this cell here corresponding to the closed loop response. So now we can execute this cell here, and then we can get the response in closed loop. Okay, as you can see here, this is for the magnitude and this is for the phase. So we have a system with a little bit of second order response here, but the damping is quite good, so we are not going to have a very high overshoot. So finally, we can get the closed loop step response of our system also using WinPython. Okay, so this means that we can inject here a step input at the input in the reference, and then see how is the transient response here at the output. Okay, and for this we use this function here, step response, which is also available from the control toolbox of Python. And then with these other functions that we have seen before from the matplot library, then we can do the plotting of the response. Okay, so by calling the step response, it is going to give us back these two arrays, which are the time array and the y out array, which are the output corresponding to the step response. So we can see this here, and then we can just click to run this cell, and then we will see here this step response corresponding to our system. We can see here that we get a warning here corresponding to the linear algebra saying that we have an ill-conditioned matrix and that the result may not be accurate. So we have to pay attention to this. Maybe our response is not very accurate because we don't have a good conditioned matrix to solve the step response. Now what we are going to do is to check this step response by doing the same analysis using LTspice. For this I have this file here, which is the same schematic as we have seen in previous videos, in the video LTspice number 7. And here what I have done is to include here this pulse voltage source to include a step response at the input of the reference. Okay, so let's see how I define this pulse. This pulse has an initial value of 0, a maximum value of 1 volt. The delay is 500 microseconds in order to do this step when the back converter has reached a steady state. The rise time is 10 nanoseconds, the fall time 10 nanoseconds, and the T-on time is 1 second, because at the end we only want to see the first part of our response, and the period is 2 seconds. We are not going to get these values never, so we can use here different values. It is not really important, and we are going to perform a simulation up to 1 millisecond. So let's run the simulation, and now we can see the output. So we can see here the first startup transient here, and then here is the response correspond to the step response. We can add another pane if we like and represent here and the step that we are injecting at the reference. Okay, in blue we can see here now the response. So even if we select here maybe 10 volts, we can see this better. So here our reference in this first part is 5 volts, and at this point, at this instant, we are doing 1 volt step to 6 volt reference. Okay, and this is the response corresponding to our system, which is quite similar to this one. Let's now, just to finish, see a couple of interesting tricks that we can do also in Spider. I'm going to delete all the plots by clicking here on this button, remove all plots. Then we have seen that we can select cell by cell, and by clicking here we can run this cell and see the result corresponding to the cell. Okay, so this is the plot corresponding to our plant, and then we can select by right click on the mouse and save the plot in our disk, or copy the image, okay, and do the document corresponding documentation. What we can do, for example, is if we execute everything here, then we can see that in the different figures we are going to see all the representations together, which is also interesting. Say, for example, that we can see the representations corresponding to the plant, the compensator, and the loop gain. Then we can just select this cell here, or these two cells, and comment these cells, so they are not going to be executed. So now I execute everything, and then I can get this interesting plot, which has in blue the plant, in orange we have the compensator, and in green we have the loop gain, both for the gain and also for the phases. Okay, so this is also interesting because we can have different plots and by selecting different cells, or just by commenting different cells. Okay, this is all now. Thank you very much for watching this video. I hope it is interesting and useful for you. Let me know if you have any comment, and see you in the next video. Goodbye now.